Hello everyone. Today we are going to discuss dielectrics and Gauss law. We are going to discuss Gauss law in the absence of dielectrics and Gauss law in the presence of dielectrics. So first, without dielectric, let us consider parallel plate capacitor, okay, for simplicity, and let the plates of the capacitor be separated by distance d, and we take d small, okay. Plates are separated by small distance d, and let us consider vacuum between the plates, and let the charge on upper plate be plus q and lower plate contains equal amount of negative charge, that is minus q. So we have this. Electric field lines starts from positive plate and terminates on negative plate, okay. So we have this, and let E naught be the magnitude of electric field between the plates, and since the distance between the plates is small, so there is no fringing of electric field lines at the edges of the plate, due to which electric field between the plates remain constant. So E naught is constant, okay. So I'm writing in vector. So we have this. Now, in order to apply Gauss law, we must draw Gaussian surface, okay. So this is a Gaussian surface. So this is a Gaussian surface which enclose charge q in magnitude, okay. So we have this. Now let us take a small elementary area of the Gaussian surface, okay. So area of this element is ds in magnitude. Now let n cap be the unit normal drawn on the elementary area, and we know vector area, okay, ds equals n cap ds. So n cap give the direction of vector area ds. So we can find from this diagram, okay, angle between vector E naught and area vector ds, or vector area ds, is 0 degree. Now from Gauss law we have this, okay. One by epsilon 0 times the charge inside the Gaussian surface, and this charge is called free charge, okay, because it can move on the surface of the plate when the electric potential between the plates is varied or is changed. So let us simplify this equation, okay. So we can write in this way. This is 1, and E naught is constant, so we can take E naught out of the integral sign. So we have this. Now We have to find this integral, okay? Now, we take that part of the Gaussian surface which encloses charge, and charge is present on the plate of the capacitor. Clear? So this integral gives area, okay, of the plate A. That is, we take that part, area of that part of the Gaussian surface which encloses charge Q, okay, which encloses charge Q. Now, area of the Gaussian surface which encloses charge Q is A, because charge is present on the plate of the capacitor having area A. So we can write in this way, okay, this integral equals A. So we have this E naught A equals Q by epsilon 0. Therefore, we can write E naught equals Q by epsilon 0 A. So we have this, okay, and let us call it equation 1. Now, we know surface charge density sigma equals Q by A. Therefore, we can write E naught equals sigma by epsilon 0. So we can write equation 1 in this form also, okay, in terms of surface charge density. So I'm erasing this, okay. Without dielectric, we have this, okay, E naught equals Q by epsilon 0 A. Let us call it equation 1, okay, and we have this also, E naught equals sigma by epsilon 0, where sigma is surface charge density equals Q by A. So we have this. Clear? Now, Q is free charge present on the plate of the capacitor, okay. So this is to be noted, okay. So we have this. Now with dielectric, okay, we draw same capacitor and Gaussian surface, okay. Now dielectric is inserted between the plates of the capacitor. Clear? So this is to be noted. It is the same capacitor, okay. And dielectrics, now dielectrics is inserted between the plates. So this is dielectric. Now due to redistribution of the charge, induced charge minus Q dash and plus Q dash, okay, are present on the upper surface and lower surface of the dielectric. So due to redistribution of charge, okay, induced charge minus q dash is present on the upper surface of the dielectric, and induced charge plus q dash is present on the lower surface of the dielectric. So q dash, so I'm writing in magnitude, okay, this is called induced or bound charge, okay. So I'm erasing it, okay. Now this is the same, okay, Gaussian surface, okay. So this is the Gaussian surface. Now the Gaussian surface contains free charge, okay, I'm writing in magnitude q, and induce, okay, charge q dash in magnitude. So let us come to this diagram, okay. If there is no dielectric, then electric field E naught is directed from positive plate towards negative plate. Now, due to induced charge, okay, electric field vector E dash is produced inside the dielectric. So this is electric field due to induced charge, okay, due to induced charge. So this is to be noted, okay, and direction of E dash is from lower surface of dielectric to upper surface of dielectric, and resultant of this, okay, these two electric field is, okay, vector E. So this is the resultant electric field, okay. So this is what? This is resultant electric field. So we have this. Now, from Gauss law, okay, Gauss law, we have this 1 by epsilon 0 times net charge inside the Gaussian surface. So we have this. So we can write in this way, okay. Net charge is q minus q dash. Let us call it equation 2, okay. So we have this. So this is equation 2. Clear? Now we have to simplify, okay, equation 2. And cos 0 degree is 1, and we take E, okay, this E constant. So we can take E out of the integral sign. And this integral is A, okay, area of the plate of the capacitor. So we have E times A equals Q by epsilon 0 or epsilon naught minus Q dash by epsilon naught or epsilon 0. So we can write E equals Q by epsilon 0 A minus Q dash by epsilon 0 A. So let us call it equation 3. Okay, so we have this. So I'm rewriting equation 3 here. E equals Q by epsilon 0 A minus Q dash by epsilon 0 A. So this is equation 3. So we have this. Now we know when dielectric is inserted between the plates, then electric field is reduced by factor K. Okay, therefore E equals E naught by K. Now let us call it equation 4. Okay, now we put the value of E naught from equation 1 in equation 4. Okay, so we can write E equals E naught is Q by epsilon 0 A, and we have K at the denominator. Okay, so we have this. So this is obtained by putting E naught from 1 in equation 4. So I'm writing over here E equals Q by epsilon 0 AK, and this is equation 4. So we have this. So I'm rewriting equation 3 over here. Okay, E equals Q by epsilon 0 A minus Q dash by epsilon 0 A. This is equation 3. Now we have equation 4. Okay, over here. Now from 3 and 4 we get this. Clear? We get this. Now epsilon 0 A at the denominator on right hand side and left hand side cancels out. Okay, so we get this Q minus Q dash equals Q by K. So we have this. Okay, we have this. So let us call it. Okay, I'm writing this relation over here. Okay, Q minus Q dash equals Q by K. Let us call it equation 5. So this is equation 6. So we have this. Now from 2 and 6 we have this. Okay, Q minus Q dash is Q by K, and we have epsilon 0 at the denominator. Okay, so we can write in this way. And we can take this K on left hand side and write in this way. Okay, Q and K is over here. Okay, we have this. And this equation is called Gauss law in dielectric. Okay, this is Gauss law in dielectric. And this is free charge. Okay, so in the presence of dielectric, okay, we have this equation. Now K, okay, which is dielectric constant, or sometimes it is also called relative permittivity of the material or medium. Okay, K is kept inside the integral to deal with the case in which K is not constant over the Gaussian surface. Okay, we are keeping K inside the integral to deal with the case in which K is not constant, that is dielectric constant is not constant over the Gaussian surface. So this is to be noted. Okay, so I'm writing this equation over here. Okay, so we have this, and this is Gauss law in dielectric. Okay, so we have this. Now we are dealing with this condition, okay, with dielectric. Now let us take equation 6. Okay, equation 6, we have this. So we can write in this way. Okay, Q dash equals Q minus Q by K. So Q dash equals Q is taken common on right hand side, 1 minus 1 by K. So we have this. Now if K equals 1, okay, this is for vacuum, so it indicates that there is no dielectric. Okay, so for no dielectric between the plates, okay, then from this relation, okay, or equation, we get Q dash equals Q 1 minus 1. So this gives 0. So induced or bound charge is 0. So we have this. And for K greater than 1, okay, that is with dielectrics between the plates, okay, from this relation we get Q dash less than Q. So it indicates that magnitude of induced charge is less than, okay, this is less than magnitude of free charge. So this is to be noted. Okay, we always have magnitude of bound or induced charge less than the magnitude of free charge. So we need to understand this. Okay, so I'm erasing this. Now again we take this. Okay, equation 5. So we have this. Okay, this is equation 5. Now we can write or rewrite this equation in this way. Okay, q by epsilon 0 a. So we have this equals q by epsilon 0 a k plus q dash by epsilon 0 a. So we have this. Okay, now q by a equals epsilon 0. Okay, we can write in this way, q by epsilon 0 ak. So we have this plus epsilon 0 q dash by a, and we have epsilon 0 at the denominator. Okay, so we have this. Okay, so we can cancel this. Okay, epsilon 0 and epsilon 0. So let me write over here. Okay, q by a equals epsilon 0 q by epsilon 0 ak plus q dash by a. So we have this, and let us call it equation 6. Okay, this is equation 6. Now we can see this ratio. Okay, this ratio is E, because we have E equals q by epsilon 0 a k. Okay, now this ratio, okay, q by a, free charge to area, is called electric displacement, okay, vector. This is called electric displacement vector. Okay, so I'm writing in magnitude and this way. Okay, this is called electric displacement. Okay, we have this. So this is d, okay, in magnitude. Yeah, and this ratio, okay, q dash by a, is called electric polarization. Okay, it is called electric polarization, and in magnitude I'm writing in this way. Okay, so it is called electric polarization vector. So I'm writing in magnitude. So this gives P, that is electric polarization P. Now we need to understand that electric displacement vector, okay, this is associated, okay, with free charge only. Whereas electric polarization vector, this is associated with bound or induced charge only. So this is to be noted, okay? So we can write equation 6 in this way. D equals epsilon 0 E plus P. So we have this. So in vector form, we can write vector D equals epsilon 0 vector E plus vector P.